Alright, welcome to my presentation titled Probabilistic Computing for the Graph Coloring Problem. I'd like to start off by recognizing that there are many kinds of mathematical problems that, till this day, we haven't been able to solve at scale with regular computing methods. And one such famous problem is the graph coloring problem. Take, for example, this blank county map of Indiana. If you wanted to color each county on this map such that no two neighboring counties shared the same color, how would you do it? Well, the most obvious solution would be to give each county its own unique color. But what if you were limited by the number of colors you could use? Could you color this map with only 4 colors? How about 3 or 2? Better yet, what if we left the plane of geography entirely and did something like this? There could be 10,000 counties and 10 million connections between them all. How can we ensure that no two connected counties share the same color? This is a type of problem that is easy to verify, but is difficult to solve. To put it more mathematically, the time that it takes to verify the solution is polynomial, whereas the time that it takes to actually solve the problem is exponential. This is the loose definition for a class of problems called NP problems, which stands for non-deterministic polynomial. These kinds of problems grow in solution space much more rapidly than a regular polynomial problem would. And you can just look at this graph over here, where x represents the number of unknowns in the problem, and you can see that the exponential function 2 to the x just goes through the roof when when x even approaches 20, whereas the polynomial function x squared is much more tame than that. And this is a really big problem for regular computers because there's yet to be a way to tackle these large-scale NP problems in reasonable amounts of time. Well, someone might ask, why can't we just keep doubling the size and the speed of our computers, right? Surely that will solve our problems. This is not a viable solution because, for one, computers are reaching physical limits, right? The size of our computer parts, like transistors, are approaching the size of literal atoms. And the second point is that even if we spent, let's say, 2 years trying to double our computing speed, adding just one more county to our map of Indiana would double our solution space by 2 again. And that would sort of negate all of that progress and all that time that we spent doubling the speed of our existing computers. So it would essentially do nothing to help us. Now, if we could somehow solve NP problems more effectively, there would be massive implications to the fields of data science, economics, artificial intelligence, and the world at large. So why not try something new? Could a new method of computation and a tailored form of hardware together tackle this exponential complexity head first? Well, one idea showing promise is probabilistic computing. Now, you may know that in regular computing, we often represent information as combinations of zeros and ones, binary. And one way of physically representing this binary is with stable magnets, which are polarized to have two stable magnetic states, one pointing north, another pointing south. And this would correspond to the two memory states 0 and 1. Now, if you put a magnet in one of these states, it'll stay there for a really long time because there's a high energy barrier that the magnet has to overcome in order to switch states. For instance, in order to get this second magnet over here to switch states to a 1 and become anti-parallel with this other magnet, like you see here, you would need to overcome the energy barrier that you see as a peak in this diagram. Now, what would happen if we lowered this energy barrier? Well, what would happen is that the magnetization of this magnet will flip back and forth spontaneously between the two stable states at a very high frequency. So 50% up, 50% down. In other words, we've just created a natural random number generator that fluctuates between 0 and 1 several times a second. And although this magnet would be useless for data storage, it is actually the key to what we call a probabilistic bit, or p-bit for short. Now, what you see here is a simple diagram of a single p-bit, and the main element of this p-bit is called a magnetic tunnel junction, or MTJ for short. And an MTJ consists of an insulator sandwiched by two magnetic layers. You have your fixed magnetic layer R, which always points in a fixed direction, and a free magnetic layer W, which could either be pointing in parallel with the fixed layer or anti-parallel. And this free layer is where we'll use the unstable magnet. Now, if the two magnetic layers are parallel, then it'll be easy for current to pass through the junction. On the other hand, if they are anti-parallel, it will be difficult for current to pass through. In other words, the magnetization of the free layer essentially determines the resistance of this element in a circuit. And this low and high resistance can be translated into a low or high voltage output. And this low or high voltage output, of course, can be understood as a 0 or a 1. Now, the really unique thing here is the Vin terminal of the p-bit. The voltage applied to Vin can essentially tune the probability of the output being 0 or 1. Now, if we applied no voltage input to Vn, the unstable magnet would just fluctuate as normal, and the output would be 50% 0, 50% 1, like you see over here. However, if we were to apply a strong positive input voltage to Vn, we could actually pin the output to be, say, 1 90% of the time, and 0 only 10% of the time. Likewise, if we applied a strong negative voltage, we could get the opposite effect. We'd pin it the other way, so 0 90% of the time, and 1 only 10% of the time. This is what a p-bit truly is. It's a tunable random number generator. And it's essentially a hardware implementation of this equation that you see on screen. And of course, this tunable property is what makes a p-bit so special. Now, things really get interesting when we start to connect multiple p-bits together. This way, the output of one p-bit could influence the output of another p-bit. And to control this influence, we can add weights between each p-bit connection in the network, using resistors, for example. And these weights would let us configure the network to have certain connections be more important than others. And with this, we can start to form a network of p-bits that act together to compute something meaningful. This is the definition of computing, after all. So what sorts of things can p-bits compute? Well, because the output of each p-bit in the network is constantly fluctuating, p-bits don't have a concrete output. Instead, the result that we're going to get will be a statistical distribution of the individual outputs you get from each p-bit over time. For instance, you can check out this histogram of the output of these 3 p-bits on the left. You can see that the probability of the numbers 1 and 6 showing up is very high, and the frequency of both are just about equal. And yeah, they're much higher compared to all the other outputs, like 0, 2, 3, 4. And these 2 numbers, 1 and 6, are in fact the 2 solutions to some NP problem that had 8 possible outputs. And it's because they have the highest frequency. And if you realize what this means that with probabilistic computing, we don't just get one correct result to our NP problem, but we get every single potential solution to a given problem in the time frame of one computation. But in order for this to happen, of course, we must initialize the network with the proper weights between p-bits in order to get a meaningful statistical distribution as the result. Now, these weights of our network can be determined by a mathematical model like the one you see here. This mathematical model, known as an Ising model, maps the graph calling problem to an expression of energy whose lowest energy state happens to be the solution to the NP problem. And because our p-bit computer is a physical system made of random magnets, and because physical systems tend to stay in the lowest energy state possible, the ground state, running this physical system of p-bits for a sufficiently long time can effectively solve the NP problem. This very principle is actually what we've been able to demonstrate, not just mathematically, but with some state-of-the-art circuit simulations performed with the industrial-level circuit simulation tool, HSpice. So let's take a look at a simple graph calling problem. We have 3 regions and 2 connections between them. What are the ways that I could color this map with only 2 colors, say red and blue? Well, there are 2 possible solutions. You could have this blue, red, and red, blue, red. And note how, the 2 connected regions don't have the same color. This problem can be solved with 6 p-bits. And this is because we need a p-bit for each region, or at least the p-bit should represent the color that each region should have. So in other words, the number of p-bits that we need is the number of regions that we have times the number of colors, which in this case is 3 times 2 equals 6. And we can simulate all 6 of these p-bits, which includes the unstable magnets and the magnetic tunnel junction, as a modular subcircuit using HSpice. We can then model the problem mathematically with an Ising formulation to determine the strength of the weights between the inputs and outputs of each p-bit. Finally, we can run a transient sweep of the entire circuit and read the output of each p-bit over time. Doing exactly that for about 5 microseconds of circuit time gave us these results. So the 2 most frequent results that we see are 25 and 38, which represented as binary. We have 0, 1, 1, 0, 0, 1, and we have the inverse of that. This basically means that, at least 25, you can see that it represents that regions 1 and 3 should have the same color, represented by 0, 1, and region 2 should have the other color, represented by 1, 0. And the exact inverse is true for 38. So we've basically gotten our correct solutions. And out of 64 possible outcomes, the probabilistic computer was able to return the two correct solutions as being the most probable ones in this histogram. And this is quite impressive, considering that the circuit is running under realistic noisy conditions. This isn't just an ideal mathematical simulation after all. We can follow the exact same approach for an even more complex graph problem now. This time we have 4 regions, and each region is in contact with every other region. So if we had 4 colors, what are the possible colorings of this graph? Turns out that there are 24 possible valid colorings of this graph. And that also gives us 2 to the power of 16 possible outcomes. That's 65,000. So will the probabilistic computer be able to filter out and return the 24 valid solutions? Well, with 16 p-bits, just 4 colors times 4 regions, this is in fact possible. Now, I can't show you the full histogram because the x-axis would have 65,000 bins that I can't fit on the screen. However, I will show you the frequency plot of the top 50 results in order. I've also displayed the top 24 results and their relative frequencies on screen. After running the simulation for only 10 microseconds, if you check each one of these top 24 results, you will find that 23 out of 24 of these top 24 results are valid solutions to our graph coloring problem. And in addition, they are all present at much higher frequencies in the output compared to the incorrect outcomes. And you can see that there's a sort of gap in frequency between the correct results and the incorrect results. And with more work over time, we hope to refine this gap to make the valid solutions even more obvious and stand out even more from the crowd. Of course, we don't even need the gap to tell us where the correct solutions are. We could just validate as many of the top solutions as we'd like with a classical computing approach in polynomial time until we're satisfied with the number of valid graph colorings we have. After all, we might not need all 24 of these valid outcomes. And of course, this will not take exponential time to do. Overall, these are astounding results because even with the realistic simulation and the added circuit noise, we've successfully simulated a probabilistic computer that found all of the valid solutions to this graph coloring problem out of 65,000 possible outcomes in a really short amount of time. And this demonstrates the capability of probabilistic computers for providing us with multiple valid solutions to a given problem in the time frame of one computation. In conclusion, we discussed the nature of the famous NP problem, the graph coloring problem. We emphasized the importance of new computing methods for solving NP problems. We also discussed the structure of a p-bit and how it can be used to effectively compute multiple solutions to a problem. And lastly, we demonstrated the results of our simulated p-bit network for solving different variations of the graph coloring problem. For some quick final thoughts, you might have wondered about quantum computing as another viable solution, but quantum computing has some disadvantages, namely that it needs to be at absolute zero to work properly. It needs ideal lab conditions, so it's very complicated to get it working properly, whereas probabilistic computing can work with existing technology at room temperature and get similar results. Secondly, we would like to figure out how to continue scaling up probabilistic computing to problems with millions of outcomes and thousands of valid solutions, because getting 24 solutions to show up accurately was already tricky, so having 1,000 solutions show up with a high frequency will definitely be even more of a challenge. And this brings up our last point, parallel computing. We're looking to find effective ways to parallelize probabilistic computing algorithms to create further speedups for solving large NP problems, because without parallelization, classical computing would still triumph over probabilistic, because we've already developed so many parallel computing algorithms for classical computing that we would need something along the same lines in order for probabilistic computing to be more effective. Finally, I'd like to thank Professor Bermel for granting me the opportunity to work with him on this exciting project and for always being able to recommend the best learning resources. I'd also like to thank my graduate mentor Jie for answering hundreds of my questions and for always being there to help troubleshoot when things went wrong. Their support has made this work possible. So, thank you all for listening.